Hey, welcome to the opening of Chapter 2. I think a lot of what we're going to talk about right now is going to feel really familiar, so I think we'll probably work through it pretty quickly. So let's get right into it. This part gets into some of the basic chemistry concepts that we're going to need to know in order to study a lot of the biological concepts we're going to delve right into this year. So the first thing is that the fundamental form of matter is in fact the atom. We mentioned this in the first vodcast when we were talking about life's hierarchy. This is as small as it gets. You can't find anything that retains that particular property and have anything smaller than an atom. Atoms are made up of three pieces. You have protons, you have neutrons, and you have electrons. And the way that it works is you've got your protons and your neutrons hang out in the center of the atom, known as the nucleus. Now, this is not to be confused with the nucleus of a cell, which we'll talk about. Nucleus just seems to mean center. And while a nucleus of a cell isn't always found in the middle of the cell, it is the central focal point because it is what controls the cell. So we want to try not to get those two mixed up. Then you have the lovely electron. And electrons are big deals. They're where the bonding happens. So the property of an atom resides in the number of protons it has, its ability to react resides in how many electrons it has, and the electrons will float, and you'll see this in a little bit, but they float all in these outer shells as they zip around the nucleus. So the atomic number. That is the number of protons that it has. It gives its identity. Hydrogen has an atomic number of 1. It's 1 proton. Helium 2, lithium 3, and on we go. The mass number, how heavy the atom is, what it's made of, what substance it has. That's your protons and your neutrons, and combined together, and so that gives it a particular weight. We're not going to spend a ton of time on that. Isotopes. Isotopes are a neat type of certain elements. They are radioactive. You'll find that you have kind of your most abundant carbon is carbon-12. It has 6 protons and it has 6 neutrons. Occasionally you get these ones that have a couple extra. It still has 6 protons because that's its identity. It's still carbon, but the neutron number varies so that you end up with a mass number of 14. And those are slight variations in these elements that are around, and they're actually radioactive. And they interact the same way as your average ordinary element would act. And radioisotopes are important because we use them, like carbon here, for radiometric dating. You might have heard about that when they talk about how they dated something to be, X number of thousands of years old. They do this by measuring how much of the radioactive carbon is still present in the material. All right, we need to have a little bit of an understanding about chemical equations. We're going to talk about reactions. We're going to talk about the types of events that occur inside a living thing, and they're all reactions. We're a big bag of chemical reactions working here, so you got to understand a little bit of the way they're put together. So we have a setup here, and this one happens to be the lovely equation for photosynthesis, and you have some certain things that you'll know. Okay, so on the left side of an equation, or on the side that the arrow is pointing away from, you have what we call our reactants. So the reactants make the reaction. Okay, so in this case we have carbon dioxide over here, and we have water over here. And of course we need energy. That's not matter, but it is part of this. I would normally take this energy though, and I would stick it on top of the arrow. And out of it you get the products. Okay, what you get, what you produce as a result of the reaction. So in the case of photosynthesis here, our products are carbon dioxide, a molecule of carbon dioxide, you get 6 molecules of oxygen and 6 molecules of water. So you can see these numbers here. What these designate are how many of each element you have, and we refer to those as the coefficients. The little numbers that are associated with the elements, so like that little 2's and the ones that are sort of subscripts, okay, those are exactly that, they're subscripts, but they are not telling me how many. It's kind of like algebra, okay? You know when you have like an equation and you say 2x equals whatever, okay? You can say 2x equals 7. We know that this 2 that's in front of the x, that tells me that I have 2 x's. Well, same thing goes here. Here's my compound, carbon dioxide, and I need 6 of them. And carbon dioxide is a compound made up of 1 carbon atom and 2 oxygens. So that's how we read the equation. Bonding, we know about bonding, but let's take a little review at some of it and get a look at what it might look like. Bonding is most important when we talk about electrons. They are the source for bonding. That's where the reactivity of an atom comes in. It depends on the number of electrons it has. So the energy levels come into play, and that's those orbits we mentioned that electrons roll in. So we call them orbitals. You know, we like to think of them zipping around, kind of like planets do around the sun, but instead of being sort of, you know, one area like our Earth around the sun, electrons go up and down and around, but they tend to remain in this sort of leveling area, and they like to pair up. So electrons, though, want to be very stable, and they're only stable when they have the right number. And if there's an oddball number of electrons in a particular outer shell, then it's very reactive. It wants to either grab more electrons or it wants to kick some out, whatever will take the less energy. Okay, so they're very lazy in that sense that they don't want to, you know, it's whatever is the less energy taxing. Is it going to be easier to kick one electron out, or is it going to be easier to pull one in? So here's what I'm talking about with those shells. First shell, when you have the first electron shell, can hold a maximum of 2 electrons. Okay, so that's the maximum that they can hold. Once you get out, and I'm not going to get really crazy with this because chemistry will handle all of this, but suffice it to say, for what we need to talk about, every shell after that will contain a maximum of 8. Once you hit 8, you move on to the next level. Okay, so 8's the magic number. And so we have that. So again, just to remember, first shell, maximum of 2. After that, we go to 8. So you can see here in something like nitrogen, there's 2 electrons in the first shell, and 1, 2, 3, 4, 5 electrons in the outer. It has a total of 7 electrons. How do I know that? Its atomic number is 7, and elements contain equal numbers of protons as they do electrons. So the valence electrons, these are the special ones. This is the biggie. These are the ones we talk about when we talk about reactions, are the valence number. They are the number of electrons that occur in the most outer level of the actual shells. Okay, so how many do you have? Do you have 2? Do you have 5? Do you have 7? Do you have a full octet at 8? And based on that, it will determine how much reactivity that atom can have. So that's the one we're going to talk about. And we like the stable octet rule. We want the outer shell to have that 8 magic number. We want 8 electrons, okay? Or we want nothing, okay? So it's kind of 8 or nothing. So it means that an atom may have to boot some electrons out, or it may take some in. So one that might be willing to boot an electron is going to be something like sodium here. Notice we've got a full first shell, we have a full second shell, and we only have 1 here in the outer shell. Well, it's going to be a lot easier for sodium to kick that electron out than it would be for it to grab an additional 7 electrons to fill that shell. So normally sodium is going to blast out an electron, but it's still sodium because it's always retaining that 11 proton number in its nucleus. So again, that's what they do. An atom's going to either give it up, it's going to gain an electron, or it may share them. And when they share, or they give up, or they take, and then they bond together, then we're talking about molecules. And what's cool about molecules is that they're chemically combined, and they take on very different properties than the atoms that make them up separately. You know, for example, water as H2O, hydrogen is a gas on its own, oxygen is a gas on its own at room temperature, but when they're chemically combined together, they're a liquid. Okay, so some common molecules. That's where you have more than 2 atoms chemically bonded together. Compound, when you have a compound or molecule, you're going to hear them interchangeably. Okay, so this could be molecule too. Not really a whole lot of difference. When you have a molecule or you have a compound, the atomic proportion is never going to vary. It's always, H2O is always H2O for it to be water. There's no variation on that amount. 1 oxygen, 2 hydrogens. Mixtures, though, are when you take things, sugar and water, and you mix them up, okay? And when you mix them up, then, you know, they're just dissolved in, but you could separate them again, okay? Kind of like what you guys did with the sludge test, is you had a bunch of mixtures in some cases, and you really just had to pull out what was there, okay? So bonding. Our very friendly ionic bond. This is bonds between 2 ions. And ions are charged atoms. This is where one's going to give one up or it's going to take one. So we have here your very standard, very textbook sodium, which is Na, and chlorine, Cl, and sodium chloride is table salt. Okay, so we have sodium, which is this nasty, noxious gas, or excuse me, chlorine is the nasty, noxious gas that could kill you by itself. Sodium is so unstable as a solid that it actually bursts and erupts into flame when it hits the air. But these two together become something that we absolutely need as ions for our body to work. These are vitally important. Sodium is huge in the transfer of signaling through our neurons, and it is that, you know, we're going to get into that later this year, but hugely important. So we have the sodium, okay, chlorine. You can see that this sodium atom, to be stable, is going to give up its electron, rendering it as a sodium ion. It's going to be a positively charged because it contains 1 greater proton than it does electron, and it's going to shoot it over. And while chlorine has 7 in its outer shell, it wants 1 more to be stable. It's going to take that electron, making it now negative. So we have a Cl minus, we have an Na plus, opposites attract, and they bind together, and now you have NaCl, and you have table salt, and they form this sort of crystal lattice. Okay, so they make this really neat patterned shape. Covalent bonding, on the other hand, is when atoms are going to share. Super nice. They're going to share their electrons instead of giving up and taking, where each atom will think that it's stable because it's going to share them. Very strong, very important to living things. Okay, so we have some examples here. Something like oxygen hangs out together with another one. It's diatomic, and it's going to share. Each one will share an electron. So you have this double sharing that goes on. We show it as a double line. Okay, so it has a double bond. But if you notice, if you count, you know, and you kind of put one hand over one of the oxygens and count them all, you have 8 all set in that outer shell. 1, 2, 3, 4, 5, 6, 7, 8 at any given time. On this one, you have 1, 2, 3, 4, 5, 6, 7, 8 on the outside at any given time. Methane. Everybody's favorite. This is the gas we all produce, sometimes some people more than others, and methane is carbon. Carbon has this lovely ability to form up to 4 4 covalent bonds. It has 4 electrons in its outer shell, so that's what it does, and that's probably the reason why it makes such a great backbone for all of our major molecules. So methane combines with 4 hydrogens, so here's these combinations. There's the 2 it's sharing in its outer shell. We're going to share, okay, 1, we're going to share them, share them, share them, and now we have 4. Single, double, triple bonds, we just talked about that. That's where 2 atoms might share, you know, might be like that, to another carbon, which then would leave you with it going like this, like that, and like that. Notice the carbon has 4 bonds that it's sharing. Hydrogen has 1 pair that it's sharing. There's the 4 pairs that it's sharing on that side, so everybody's happy. Triple bonds would be exactly that. There'd be 3 lines between 2 atoms instead of 1 or 2. So a little formula talk, just real quickly. We're not going to take a ton of time with it. Empirical formula, this is where you get sort of the reduced version, reducing down the number of elements that maintain the same proportion in each. So for methane, you're going to have something like CH4. There's 1 carbon, 4 hydrogens. You can't reduce it down any more than that. Benzene, its reduced empirical formula is a carbon, 1 carbon ratio to 1 hydrogen. However, the molecular formula is very different. This is the way, how do these molecules actually occur in their proportions and their ratios out in nature? Well, methane, same deal, CH4. Benzene, on the other hand, is C6H6. So it is, that is how you find it out in nature. Now, the structural formula gives us an opportunity to look at how it might actually be shaped. Okay, methane looks like that. Okay, it takes the hydrogens right off of the carbon. Benzene, on the other hand, formulates itself into a ring shape, and you can see every other carbon shares a double bond with itself, and that's how it occurs out in nature when we find it. Polarity. Sometimes molecules don't share their electrons equally. Some get a little greedier than others, and as a result, you're going to have this charge region that's going to occur. We have, when there is no charge and everything is shared, all hunky-dory and everything's equal, we call that nonpolar. Okay, polar applies, or excuse me, not applies, implies that there are regions. So something like this, and where you're going to have basically oxygen, O2, hanging out. Everything is shared happily. Everything's uniform. There is no charge or no charged region to the molecule. Polar, on the other hand, you're going to get unequal charging, and you're going to get some partial charges as one atom pulls the electrons a little closer. That's going to be a little bit more negative. One pulls it a little further. As it pulls those electrons further away from the other atom, that one becomes a more positive region. Textbook example is water. Oxygen here tends to, hang out with those electrons and pull them just a little bit closer to themselves, and you get a positive region there where you're going to, or excuse me, negative, and you're going to get positive regions here by the hydrogens. So it looks like that. Still, the net charge is 0. There is no charge. It's not an ion, but there are regions of partial charge just because of oxygen being a touch greedier with those electrons. And as we begin to wrap this up, hydrogen bonding is super duper important. These are your weak interactions. These are just like tiny little, you can think of them like little magnets in a molecule that are just going to hold little areas together so that it retains really important shapes. And so it takes this little attraction between molecules or the functional groups of a single molecule and holds them together. So it can be between 2 molecules, like water. Okay, so we could have water get some hydrogen bonding action going on to hold it together as you get the weak interaction between a hydrogen and an oxygen, normally designated by those lovely dots. You have the most negative atom. That's going to be the one that's going to interact most often with the hydrogen. Obviously, opposites attract again, so that's what's going to happen there. And these are usually polar to polar covalent bond attractions that happen. So here's just a little picture of one that occurs in a very important molecule for us, DNA. All right, DNA has this beautiful twist. It's called a double helix, but it's made up of two sides. There are two molecules here, and they're held together down the middle like a ladder, but the ladder is held together in the middle here by a hydrogen bond. And that hydrogen bond is an association between a hydrogen on one and a nitrogen on the other. So it, or it could be an oxygen as well too, but it holds it together. And that's what allows our DNA molecule to retain that beautiful double helix shape and maintain the two halves. And here's the last little bit. And I know we mentioned this a little bit, but these bonds are really, really weak by themselves. But collectively, they're very, very strong. So they become very, very important, and you'll see that importance when we start talking about proteins. So until we meet again, guys, we'll see you in class. Bye.